IP version 6 networking. In this nugget, we address IP version 6. This follows a lot of the same principles that we looked at with IP version 4, except that the addressing, although it's similar, it uses hex instead. So hex actually boils down to the fact that it's still all binary, but it's just harder to read, that's all. So we'll take a look at the addressing with IP version 6, as well as the various types of addresses you can get. Different addresses have different purposes, so we'll take a look at those. We'll also look at transitioning from IP version 4 to IP version 6 and some of the technologies that are used to do that, and name resolution, which primarily that's going to just involve quad A records. We'll also take a look here at troubleshooting, and there's not a whole lot to say there because most of the tools that you can use with IP version 4 you can also use with IP version 6. In our last nugget, we took a look at IP version 4, which remember is 4 octets, so it might be, something, 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 okay, all separated by decimals. Well, what's the difference between IP version 4 and IP version 6? I mean, is it something like this, 6 octets instead of 4? No, that's not it at all. Okay, this is not how that works. What IP addressing with IP version 6 is it's a dramatically larger number. Now, with IP version 4, we didn't really address this in our last nugget particularly, but we're pretty much out of all the public addresses that can be used, even though there's 4 billion of them, because of the way it's divided up and because of inability to anticipate how things would change in the world and with the internet and all. The original authors of IP version 4 never realized that they could run out of addresses if they had 4 billion. Well, they did, and that through no fault of their own. So with IP version 6, they've dramatically increased the bit length from 32 bits on an IP address for version 4 address to 128 bits. So now we don't have just 4 billion addresses. We have whatever that number is. I have no idea what this is. I mean, I can go so far. There's hundreds, thousands, millions, billions. See, trillions, quadrillions. I don't know. There's septillions in there somewhere. And then the rest of this stuff, I don't even want to try to pretend like I can pronounce or understand what that is. But you can see that that's a gigantic number. Somebody has estimated that they've tried to express this in a lot of different ways so that humans can comprehend it. But I heard one estimate saying that this is such a big number that each human on the planet could have 4 billion of these addresses on their own. So that's how big of a number this is. And it's pretty staggering and difficult to imagine that we could ever run out of IP addresses with IP version 6 addressing. Now, this is going to still use binary numbering. Okay. However, instead of using binary and decimal only, this is going to use 8 groups of 4 hex positions. Okay, 8 groups of 4 hex positions. I'll show you some examples of that here in a little while. And certainly, they could have decided to stick with just binary in this. It's just that it would make such a long number so difficult to read. I mean, they've got 128 bits, and if you try to separate out all the ones and the zeros and all of that, it's just one of those things that if you do it too long, it's one of those things your mother told you would make you go blind. You just can't look at all those single-digit bit positions. So to make it somewhat easier, it's still kind of hard to read sometimes, we use hex instead, which uses the numbers 0 through 9 and A through F to give us a total of 16 possibilities per bit position. So here let's take a look at an example of IP version 6. Remember I said it's 8 groups of 4 hex positions. So here's group 1, group 2, group 3, 4, 5, 6, 7, 8. There's 8 different groups. And then in each one of those groups, each one of these bit positions here, so let me use the right tool, each one of these bit positions represents 4 bits. So that F that we see right there, that's actually 4 binary bits that are kind of consolidated into that letter F. Same with D. That's actually 4 binary bit positions. And it's the same is true of all the rest of these. Of course, the 0 here, you can guess right away that that would equivocate to 4 zeros in bit positions. All right? But what about these, some of these are self-explanatory. The 1, okay, what would that be? Well, in binary, let me actually make some space, some scratch pad space here. If we were trying to do a 1 in hex, that would equal 0001 in pure binary. Why? Because remember in binary, the rightmost position is a 1, and then this is a 2, and this is a 4, and this is an 8. So if I've got a hex value of a 1, then I know that that can be the only bit that's turned on. Okay, let's take a look at a PDF document I've prepared for you as well. I got this really from easycalculation.com at this URL. I was going to create this from scratch, but there's really no other way to do it. There's only one set of facts here. You can't really make your own facts. So, for example, again, here we see the 1, and like I just told you there, actually here, the hex value of 1 equals a decimal value of 1 and a binary value, much like what you see right there, or exactly like what you see there. And this goes all the way up until you get to 9. So, for example, here we have a 1 turned on plus the 8 position, so obviously that adds up to 9. And so in hex, we would see 9 here, and in binary, or decimal, we would see 9 there as well. This is where it gets to be a little bit more tricky, because normally you look at the letter B and you don't really think of a number. Same with any of the rest of these, but you can use A through F. The reason for this is because in hex, you can't use double digits in any of the spaces, because then would that really be, if I wanted to enter in a 10, would that actually be a 10, or would that be a 1 and then in one position and a 0 in the next position? Well, there's no way to tell. So you have to use it single expressions of whatever that number is supposed to be. So then you move off of single digits, and you have to move to double digits being represented by letters. Now, in decimal, the number 10 would be equal to this in binary. So you'd have the 2 plus the 8 would equal 10, right? In hex, you represent a 10 with the letter A. And you can see all the rest down here as well, and adds up to a total of 16. And it's 16 because even though it says 15 right here, remember we're starting with 0. 0 is a number in this kind of a calculation, what we call ordinal numbering. Okay, so this is available for you also on nuggetlab.com if you want to kind of just review that and get used to how hex numbering works. It is a little bit difficult to get used to, though. It kind of takes a little bit of practice. Also, there's a couple of rules involved with expressing an IPv6 address. Number 1, you can eliminate consecutive zeros with a colon. Okay, in quote. Not in the quotes, but I just put the quotes there so you would identify what that is. Okay, it's a colon is what you'll use, and you can drop leading zeros. And in our example here, we have done just that. So, for example, here we have no leading zeros in the first group, no leading zeros in the second group. In the third group, oh yeah, hey, look, there's 3 leading zeros. So we can represent that with just nothing. We can just drop those. Okay, so we separate these all with colons instead of periods, and we just drop the leading zeros. Well, how about this? Now we have, after this 6 there, we have all zeros through this whole consecutive set of 3 groups. All right? How do we represent those? Well, you can kind of shorthand that. You can type them all in if you want, but you can also shorthand that to indicate that there's all zeros there in this section right there, and then it resumes again towards the end. And then we have different types of IPv6 addresses as well. Remember, with IPv4, you had public and private and a PIPA, those sorts of things. Well, we have also those kinds of categories of addresses with IPv6. The first one you'll see will be a global unicast address, and that's the most like the public IP addresses, so to speak, that are routable on the internet in IPv4. So these global unicasts are likely to be used in public environments such as the public internet. And there is an IPv6 internet that is emerging. In the United States, we don't have it too much, but in parts of Asia, where they were really short, got the short end of the stick with IPv4 addresses, many parts of Asia have started to switch over to IPv6. Anyway, with this, what happens is, in the addressing, you'll see the first 3 bit positions will be a 001. Well, you might look at this and say, okay, the first 3 bit positions, so that's the first bit position, that's the second bit position, that's the third bit position, right? Wrong. That's not how that works. Remember, each one of these positions in the group in hex will represent 4 bits. So this first group, this first position right here actually represents 4 bits. 0, 0, 1, 0. This is the binary position of a 1. This is the binary position of a 2, so it's turned on. That's why we got the 2 right there. Okay? So this position actually represents 4 binary bits. And then you continue on. Usually you're going to see these global unicast addresses represented as 2000 or 2001 when you see them, and you want to visually identify whether or not it's a global unicast address. It'll start like that. There's other numbers that could be used in the public internet, whatever you want it to be pretty much. But some of the ranges are reserved for future use and for other purposes like that. And it's just kind of common that this is what you'll see as the de facto standard. There's also the link local addressing. This is very much like a PIPA addresses in IPv4. Now, remember with IP4, this is considered bad if you get an a PIPA address. Oh no, the DHCP server is down. Now what do we do? So in IP version 6, you're supposed to get a link local address, even if you also have a DHCP server doling out addresses and configuration to all of your clients. So you're always going to get these, even with DHCP. And let me show you an example of what they might look like. These will always start with FE80. So notice here my link local IP version 6 address, FE80, and then we have : and then 3C, 39, and then so on and so forth on down to the end there. By the way, the %13 identifies the number of a unique number for this interface. That's just what that's for. But anyway, here we have. Let's have a pop quiz with this. How many consecutive zeros are in this? Can you tell by looking? Yeah, actually you can, because we have two consecutive zeros, or we have consecutive zeros here represented by the two colons. And we normally we're supposed to have 8 groups, but how many groups can we actually see? 1, 2, 3, 4, 5. Therefore, this : must represent 3 groups of consecutive zeros. All right, so that's just kind of one way that you can put all that together. Now notice that this FE80, this last position here, has all zeros. So in binary, what would that look like? Well, it would look like 0, 0, 0, 0, 4 zeros. And what happens here is after the 8, you'll string together. If you were to look at it in binary, you would have 54 bits of zeros. Actually, that includes part of that. Okay, so you'd have 54 bits of zeros. You'll also see something called unique local addresses. This used to be called in the old days site local, although Microsoft still refers to it as site local. That's actually a term that comes from an older RFC, which has since been deprecated in favor of some newer ideas. So now technically, if you want to keep up with the proper vocabulary, it's unique local. But if you're speaking Microsoft terms, it's still the old site local. This is very similar to a private IP version 4 address. Remember, with those addresses, they're usable only on the local network, but on the public internet, they're not useful. Okay? Well, this is similar to this. Also, these unique local addresses will start with any of the following: FC00 and then : which means there's a bunch of zeros after that. FD00 and again : and these two right here are the official current RFC, okay, which is again request for comments. Now, if you're looking at Microsoft documentation, they will tell you that it should be something that starts with FEC0 : Again, this is based on the old RFC, which came out in 1995. It's 15 years old. In reality, this is not what we are using in current networks right now. And probably if you talk to people that are experts with Cisco, like our own Jeremy Chowra here at CBT Nuggets, he will tell you that this is deprecated pretty much. I'm not saying it wouldn't work, but it's not what we should be using anymore. We should be using one of these instead. And then multicast addresses are pretty easy to spot. They start with an FF. And by the way, if we haven't discussed multicasting, that's where you can issue a certain message. Usually it's something like a video stream or some kind of a broadcast like that. Or it could also even be with WDS, which you talked about early in our series. It can use multicasting to send the same message out simultaneously to multiple recipients. So that's what that is. And then we also have loopback addresses. Now, in IP version 4, let me get my command prompt open here. In IP version 4, we could ping a loopback address as well. Do you remember what that was? Yeah, it was ping no, I forgot, 127.0.0.1. And that was our loopback address. The fact of the matter is, though, did you realize there's actually 16 million different loopback addresses? That's right, because 127 is a Class A address, and it's not really technically 0.0.1. It's the entire range. So I could also ping 127.255.255.254. That's the last address you can use. And look, I can still get an address from that or any address range in between. So it's a pretty huge number. So we have 19, what is that? 16 million different ways to ping ourselves. But in IP version 6, they made that a lot more efficient and did not use so many wasted addresses there, because you really only need one address to ping back, to loop back. So we now ping : 1. That's it. Okay. By the way, with ping, it's a little bit off topic, or I guess it's on topic. We could ping. You can also identify whether you want to use version 4 or version 6. So if I wanted to ping for sure with version 4, I could say ping -4 and then the host that I want to reach. and then it would give me a reply back on that IP address, which is IP version 4. And then if I wanted to change that to IP version 6, then it will reply back with the link local address of that host and the interface that link local address can be found on. Okay, so that's how we can work with that. Now, moving forward with the public internet and with corporate networks trying to interoperate across WANs and with their other networks and so forth, we've got to figure out a way to transition from IP version 4 to IP version 6. Now, in the reality of this, there's still a lot of organizations that really don't have any plans to go to IP version 6 because you can use so many private IP address ranges, such as the 10 dot network, that you can divide that up virtually however you want to, and it works out just fine. However, there are some organizations, some universities, some government organizations, and foreign countries outside of the U.S. anyway, that do have plans and are already in transition to IP version 6. So this is something that we do need to know something about and how we're going to make that transition. One of those ways would be by using something called dual stack routers. Now, with a dual stack router, it'll handle addresses that start with zeros, all zeros, and then at the end it'll have the actual dotted decimal notation. So it might be 172.27.9.2, something like that. That's just what the W, X, Y, and Z are, dotted decimal notation. Okay, so it starts with all zeros and then it ends in the IP4 translation, so to speak. And these dual stack routers can handle traffic that comes in, for example, on IP4, but then when it has to send it to an IP6 destination, it needs to convert it to this kind of an IP version 6 address. Okay, so that's kind of how that works. And dual stack routers are useful for handling that transition back and forth between 4 and 6. There's also tunneling that can be used. There's two different kinds. There's starting with an IP version 6 address and tunneling to a version 4 network, a destination, or vice versa, 4 to 6. Okay, when you use tunneling, the hosts, the addresses that are going to be used in this are going to start with 2002. And that will be your visual clue that it is being tunneled using 6 to 4 or 4 to 6. And of course, the 2002 would only relate to the IP address that's being identified in the 6 part of that. Okay, if I can make an arrow there. There we go. In the 6 part of that. There's also ISATAP. This stands for Intrasite Automatic Tunneling Addressing Protocol, which is sure a mouthful. That's a lot of acronym right there. But anyway, what this allows us to do is it allows IP6 to use ISATAP to allow two nodes to communicate over an IP4 network. Okay, so I might have two hosts. Maybe this is an IP6, I'll put 6 up here, host, and then this is an IP6 host, and we need to communicate with one another, but the router in between, or the network, or whatever it is that's in between here, is a version 4 network. So the way that can happen here is, again, it could use tunneling, could use it, maybe this would be a dual stack router that can handle this, or it could be using ISATAP. And if that's the case, then whatever network device here in the middle, it's going to have to support this, and it will take the IP version 6 address, and it will convert it into this kind of a format where in the middle here, you'll have 64 bits that are IP version 6 bits, and then you'll have 32 bits, which are 5EFE. So you'll see that visually in the middle and know that it's an ISATAP address. And then on the end, you'll have the 32 bits that are the IP version 4 address. Okay, so it takes it as a 6, converts it to a 4, and then places it back on the wire here at the destination, again as a 6. And by the way, one thing that's kind of interesting about this as well is the last bit of this in the address. It can be expressed either as hexadecimal or as dotted decimal. Either one will work with that. Also, there's teredo, which is kind of weird because the term actually comes the term actually means a worm that eats through wood. Okay, but that has to do probably with the kind of tunneling that it can use. What it does is it'll send, again, IP version 6 packets as IP version 4 UDP packets, and that would be the case if we are trying to communicate again from an IP version 6 host to a 4 destination this time. Okay, so over here this is IP version 6, and maybe this is where we are, and we're trying to communicate with this host right here. In the middle, there has to be a Teredo server somewhere in the path, and it has to be able to handle the IP6 packet and then convert it to an IP version 4 UDP packet to arrive at its destination. There are actually several Teredo servers out there on the internet, many of which are serviced by Microsoft themselves. This also, by the way, Teredo also serves to work around IP version 4 NATs, because when you get to the destination here, what NAT does is it will use a public IP address on our public interface right here, and it has to be able to turn that around and return traffic to its original source. Well, Teredo allows us to work with that, whereas if we did not have Teredo, then we would have to somehow manage to get this traffic back out to the IP version 6 host, and there's really no facility for that in IP version 4 network address translators. So again, Teredo is very useful for that as well. For IP version 6 connectivity, you do need to make sure that you have DS name resolution properly configured. This is true for both IP version 4 and 6. But remember, for IP version 4 in DNS, you would configure what we call a host or an A record. In IP version 6 DNS, you would create a host quad A record, is what we call these. Okay, so let's go ahead and take a look at how that would look in the interface. You don't need to memorize DNS or know how to configure it particularly, but you can see here that this is my own local domain here that I'm working with, and I've already got some registrations that appear here. For example, this is the host record that was dynamically created by my computer in DNS, because DNS supports dynamic update. So it created a host record for this host, and this is the fully qualified domain name, and it's got this IP address. Okay, and if I wanted to create one for my quad A records for IP version 6, only IPv6 uses quad A's, and so I'd enter in the name of the host, and this would be again James Win 7 -64, and then I'm going to paste in a IP version 6 address, for example, and then we would just click on Add Host. Now when I do that, notice that it identifies that it was an IP version 6 address, so it automatically creates a quad A record for me as opposed to an IP version 4 host record. So this is just a little differentiation that you can make there. I'm going to go ahead and delete that for the time being. A differentiation that you can make to identify which ones are A's and which ones are quad A's. Also, when you configure the network properties for TCP/IP version 6, you can do that a couple of different ways. So if I go to, let me just go to any host, let me go to this one. And if I right-click on here and go to Network and Sharing Center and once again go to change the adapter settings, then we can see that we can still right-click here, and just the same way that we configured IP version 4, you can do the IP version 6 as well. So I double-click on that, and I use the following IP version 6 address, and I'm going to again paste in an address that I've been using. It's a lot easier than typing all of these colons and stuff in here. And then there is a subnet length prefix, just like I talked about, the fact that there's subnet masks in IP version 4. Well, there's also subnet mask here for IP version 6. And I could give it a default gateway, which I'll let's just say that that's going to be 11 or something like that. And then you could also enter in the DNS server's address as well. And I don't have to happen to have that off the top of my head, but that's just how you would configure it. It's really the same as with IP version 4. You just kind of fill in the blanks there, and you'll be fine. Then the other way we could do this would be if we wanted to use the net shell command. Now, net shell, as you can see right here, is net shell right there, is a very powerful command. You can do virtually all IP configuration and manipulation using net shell. In fact, there's certain things you can do that there is no interface for, so you have to do it using net shell. And it's a pretty advanced tool. It involves a lot of different syntax. But I could configure my IP version 6 address here as well by doing net shell, and then you would type interface, but you can also abbreviate just int, IP version 6, and you could also do IP version 4, but I'm doing 6, set address for this interface, which is the local area connection, and set it to the same address that I had in my clipboard, and then I would just press enter, and then we would see that we now have it. And if I do an IP config all, then we'll see up here close to the top that it did indeed accept that address. At least I think it did. It should be in here somewhere. Oh, it's this one. Okay, so it's where'd it go? Oh, it's right there. FD00 and then all of this. Okay, that's the IP version 6 address that I just configured. When it comes to troubleshooting TCP/IP version 6, it's mostly the same as the tools that we already showed you in the last nugget for IP version 4. You just have to type in a -6 in order to use IP version 6 with the tool. For example, I could do a trace route with -D, which means just don't resolve the name, to -6. That means I'm using TCP/IP version 6 to DC1. I would go for a more distant host that I'm trying to work with, but my ISP doesn't support IP version 6 yet, so I can only stay within my network. But here we would go like this, and we can see that it was able to trace it one hop away. Similarly with ping, I wanted to ping -6, DC1, then that also would force it to ping with TCP/IP version 6 as opposed to IP version 4. And again, most of the other tools have similar ways of using IP version 4 instead. Also, a unique local address is going to help us kind of categorically because, and that's what BC is, because my kids have me texting a lot now, so I happen to sometimes text abbreviate stuff. So the unique local will help because there's no manual configuration. A big part of problems with static addresses is human error in entering in the addresses. And that's just with TCP/IP version 4. And you can imagine that with IP version 6, sometimes the addresses being so long and with so many colons in between and everything, someone's going to someday put a semicolon in instead or something like that, or leave something out. And for many of the interfaces, it'll kick you out and say you've entered in a wrong value anyway, but you never know. I mean, there's a lot of room for human error there. But since we have unique local addresses, we can at least communicate on a local network without having to be concerned about that manual configuration. So again, most of the troubleshooting for IP version 6, same that you would have done with IP version 4. In this nugget, we took a look at IP version 6 networking. We took a look at the addressing. First of all, remember, it's all in hex, and each one of the positions in a group will represent 4 binary bits. So it really is kind of a very compressed format, sometimes a little bit difficult to read, but it'll help if you get a grip on how those hex numbers actually come to be. And I have documents for you again up on nuggetlab.com to help with that. We took a look at the various types of addresses, such as link, local, globals, all those sorts of things. And we also looked at IP version 4 and transitioning to IP version 6. Because sometimes you'll have to send a packet from an IP6 network through an IP4 network to a destination IP6 network, or all vice versa. So it can be any combination of those things, and a lot of those technologies that we looked at will help with that transition. And then we looked at name resolution as well, primarily with IP version 6. That simply involves having a quad A record. Fortunately, most of the troubleshooting tools that you could use for IP version 4, such as traceroute, path ping, all those sorts of things, will be the same in IP version 6. You might just have to also add in a -6 to force it to use TCP/IP version 6. Well, I hope this has been informative for you, and I'd like to thank you for viewing.